Hello and welcome to yet another lecture on power generation and economics, paper code EE704C. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is unit commitment solution methods, that is dynamic programming solution. Lesson objective. After the end of this topic, students will be able to understand the concept of unit commitment solution using dynamic programming. Today, I will discuss about the part 2 of dynamic programming solution. So, dynamic programming solution part 2. In our in my previous lecture, I have discussed about the dynamic programming solution, that is part 1, where for a particular example, the total cost that is calculated where we concern the priority list method or priority order scheme, that we have denoted it as a case 1. So today I will discuss about the case 2 and case 3. In case of the case 2, I will discuss about the complete enumeration process. In case of the case 3, a constraint that is called minimum up and minimum downtime will be included to see how the cost of a system or how the cost of or the total cost, how it is varying by inclusion of that particular constraint. So the example 1, that is the previous example that I have taken. So this is known to us that for this example, the complete search range will be used, and we will study the 3 cases. From the 3 cases, the first is the priority list schedule that we have already discussed, and the second is the same example with complete enumeration that we will discuss today about the complete enumeration process. So it is clear that for both of the first 2 cases, we ignore the hot start cost and minimum up and down times. The third case, that is include the hot start cost as well as the minimum up and down times. So for the first 2 cases, we are ignoring the hot start cost and minimum up and down times. But in case of the third case, that is denoted as case 3, we include the hot start cost as well as the minimum up and down times, this constraint that we will add in order to find the total cost. So we will commit 4 units, and in order to serve 8 hours of load pattern. So the example 1, that data on the units and the load pattern are, there is a table for the unit characteristics, load pattern, and the initial status for the cases are given in the example. So this is given that there are 4 units, that is units 1, unit 2, unit 3 and unit 4. And their maximum and the minimum output in megawatt are 80, 250, 360 for unit 1, 2, 3 and 4, and minimum 25, 60, 75 and 20 for unit 1, 2, 3 and 4. So incremental heat rate, that is BTU per kilowatt hour, is 10440 9000 8730 11900 for unit 1, 2, 3 and 4. So the no load cost, that is rupees per hour, is 213.00, 585.62, 684.74, 252.00. Full load average cost, that is rupees per megawatt hour, rupees per megawatt hour in rupees per MWH, that is known as watt hour, that is average load, that is 23.54, 20.34, 19.74, 28.00 for unit 1, 2, 3. So today, for our third case, we will consider this particular part. This is the minimum times, that is minimum uptime and minimum downtime in an hour. There is uptime for unit 1 is 4, unit 2 is 5, unit 3 is 5, unit 4 is 1. Downtime, unit 1 is 2, unit 2 is 3, unit 3 is 4, and unit 4 is 1. This means that when a unit, say unit 1 is in operation or say unit 3 is in operation, it must be operated for the 5 hours. And if it is offline, it will be offline for 4 hours. So minimum up and minimum downtime means you cannot start a unit when it is in minimum downtime. Before end of the minimum downtime, you cannot start or commit a unit. Or you cannot shut down a unit when it is in running condition or when it is in up condition. You can't able to shut down that particular unit. So these constraints today will include in our case 3 part. This entire constraint, that is the minimum up and the minimum downtime, will be included in our case 3 part. So the unit, that is unit 1, 2, 3, 4, the initial conditions, that is hour offline and hour online, that is 5886. Startup cost, that is hot start 150, 170, 500 and 0. Cold start 350, 400, 1100 and 0.02. And the cold start hour is 4550 for unit 1, 2, 3 and 4. So another part is the load pattern. So we have seen that we have used 4 units and 8 hours of load pattern. For hour 1, the load demand in megawatt is 450. For hour 2, it is 530. For hour 3, it is 600. For hour 4, it is 540. For hour 5, it is 400. For hour 6, it is 280. For hour 7, it is 290. For hour 8, it is 500. This is the load pattern. So we will start our case 2. Our case 2 is the complete enumeration process, where each of the states, that is from the state 0, from the state 1 to state 15 will be included. That is called the complete enumeration process. So complete enumeration, that we will strive with a limit of, say we have 4 units. So for each hour, that is 2 to the power 4 minus 1, that is 15 dispatch each of the 8 hours. So for the each hour, there are total number of dispatches is with a limit of 2 to the power 4 minus 1, that is 50. So we have 8 hours of load pattern. So there are is a theoretical of maximum possibilities are 15 to the power 8, that is equal to 2.56 into 10 to the power 9, that is the maximum possibilities for 8 hours of the load pattern. But it is fortunately that most of these are not feasible because they do not supply sufficient capacity and can be discarded with little analysis required. Because so there are a number of possibilities are for the 8 hours. So for each hour it is 15. For 8 hours it is 15 to the power 8. That is 2.56 into 10 to the power 9 possibilities. But among those possibilities, we have to find which possibilities are feasible one, because it is seen that the most of the possibilities can't be able to meet the load demand. So those possibilities can easily be neglected, or little analysis of those possibilities are required. So now we'll study the case 2. So in order to study the case 2, we will remember, first we will remind that we will do the complete enumeration process we have already done, and all the calculations that we have seen in our previous discussion, that is the calculation of the total cost, that is the summation of production cost plus summation of transition cost, or we can say it as a startup cost plus summation of no load costs. And for each of the state and for each of the hour, we will calculate. We have calculated that particular cost that is required for each state, and for a particular hour, among those costs, which one is minimum, we will select that. We have selected that particular cost. So again, the calculation that we have seen in our previous discussion, there is a total cost is the summation of production cost. Total cost is the summation of production cost, transition cost or startup cost, and the no load cost. The calculation is remain same here. But if I see our previous discussion, the feasible states were 5, 12, 14 and 15, and we have neglected the 13th state, but it is also meeting the load demand, that is 610. So the 13th state is neglected because in our case, in case 1, we from that particular, we just give or we use the conception of priority list scheme. But in case of the priority list scheme or priority order, we just omit that particular 13th state. But here we haven't have to include that 13th state because we are doing the complete enumeration process. So the 13th state must be included, and it is included here. So the example 1, that is the case 1 and case 2 for the first 4-hour load pattern we have seen. This is our load pattern for the first 4 hours. For the hour 1 it is 450, and the hour 2 it is 530. For hour 3 it is 600. For hour 4 it is 540. This is the load pattern. And this is our state number 15, 14, 13, 12, 11 and so on. and corresponding unit status. 15 state means all the 4 units are in operation. 14 state means unit 1, 2 and 3 are in operation. 13 state means unit 2, 3 and 4 are operation. 12 state means unit 2 and 3 are in operation, and so on. And the total capacity, that is the summation of or the maximum capacity of the units, that is 690, that we have already seen in our previous discussion. For 15 state, for 14 state it is 630, for 13 state it is 610, for 12 state it is 550. So it is clear that the load demand, this is the startup cost, that is hour 0, that is called the startup cost. When load demand is 540, that I have told there are many combinations which can't able to meet the load demand, and those combinations are not all. Combination means that which combinations of units are on. Say for 15 state, the 4 units are on. Say for the 13 state, the unit 2, 3 and 4 are on. This is called the combination, and which combination can easily serve the load demand. And it is seen that 12, 13, 14 and 15 state or the combinations, the unit status can serve the load demand. So it is the load demand, there is a startup cost. This is called the startup cost at hour 0. So if I remember the previous discussion of our previous discussion regarding priority scheme, so it is even that for hour 1, that is hour 1, it's a 4-hour load pattern we have given. For hour 1, the states are 12, 14 and 15 using the conception of priority list scheme, but here for the case 2 we are including the complete enumeration process. So in case of complete enumeration, we are including another state called state 13. So this is the hourly operating cost by total cost. So if I remember the calculation will remain same. It is 9208 by 9208 for 12 state. For step number 14, it will be 9493 by 9843. For step number 14. For step number 15, it is 9861 by 10211. And we are also including the step number 13 here. Is 9576 by 9576. So same in the case of the hour 2, that is 11301, that we have know how we have calculated it by 20860. So in this way, the hour 2 is calculated, hour 3 is calculated, and hour 4 is calculated. So in this way, the hour 2, hour 3 and hour 4, that all the hours, the cost, that is the hourly operating cost by total cost, that is the hourly operating cost by total cost is calculated. So that is the hourly operating cost by total cost is calculated in particular. And it is seen that for hour 1, the state 12 is the most feasible state considering the economic concern. For hour 2, that state 12 again is the feasible. For hour 3, the state 14 is feasible, that is 14. And for hour 4, state 12 is feasible with the help of minimum cost. And in this way, the entire case 2 is designed for the case 1 and case 2. Because case 1 is the priority list scheme, and case 2 where the complete enumeration is there. And for that particular part, for that particular reason, the 13th state is included here, because previous discussion we have seen that 13th state was omitted because we are considering on the list priority scheme. We are considering on the priority list scheme. So here we are including the complete enumeration, means 13th state, the total capacity of generation capacity of 610 and able to meet the load demands or the load pattern that we have seen. So here, if I see that particular part, rather going to the 14th state, it is just moving from, rather in this case of the complete enumeration, where in case of the priority list method, from state number 12 it is going to state number 14 at hour 3. From state number 12 it is going to state number 14 at hour 3, depending upon the priority list scheme, in order to meet the load demand of the third hour. That is, for the first 2 hours the load demand is 450 and 350, but the third hour the load demand is 600 from the table or the data that we have get. So in order to meet that, if I use the conception of priority list scheme, as the load demand was 600, so 600 means 550 load demand at the state 12 cannot able to meet the load demand of 600. So now using the conception of priority list scheme is going to the, for the priority list scheme, this state number 13 is omitted, this is not there, so it is moving from 12 to 14, but the capacity is 630. So it is moving from 12 to 14. But when I use the conception of complete enumeration, that state number 13 can easily able to serve the load demand of 610, it is because its capacity is 61, the load demand of 600 at the at third hour, because its generation capacity is 610. So rather moving from state 12 to 14, it is moving from state 12 to 13, moving from state 12 to 13, and again come back to the state 12, where the load demand is, or the load demand is 540, so generation capacity is 550. So rather moving from state 12 to state 14, it is moving state, rather moving from state 12 to state 14, it is moving from state 12 to state 13. And because if I see that particular load pattern where the first hour all the 4 units are on, for the second hour, when from for the first, we can say that for the first hour the 4 units, for the state 15 the 4 units are on, for the state 15 the unit 1, 2, 3 is on, where unit 4 is off, and where in case of the state 13 where unit 1 is off and 2, 3, 4 is on, and state 12 unit 2 and 3 is on. So when I move from state 12 to state 13, we have to on the unit 4. But unit 4 is the most inefficient unit. But if I do the cost calculation, we will see that rather than for the hour 3, at hour 3, rather than turning, what we will do, we just on the less efficient unit for the our state 12, it is seen that unit 2 and 3 is on, and state 13 units 2, 3 and 4 is on. So rather than we are, when we go from state 12 to state 13, we turn on the less efficient unit, that is unit 4, rather than turning on the more efficient unit, unit 1 in that particular period. Because we are moving from state 12 to 13, because we are doing the complete enumeration. Rather than turning on the unit 1, that is at 14 state, we are turning on the less efficient unit, that is unit 4. And in this way, we meet the load demand for the third hour. Just concentrate on the third hour. In case of the third hour, this is very important. In case of the third hour, the load demand is 600. So with the help of complete enumeration, we are moving from 12 state to 13 state, because previously with the help of priority list method, we are moving from 12 to 14 state, means we are turning on the first unit. Now we are moving from 12 to 13 state, we are turning on the less efficient unit, unit 4, rather than opening the, rather than commit the unit 1 at hour 3. So because of that, in order to, if I do the cost calculation for each state, we will see that here the true optimal commitment is found, that is the less expensive to turn on less efficient picking unit, that is number 4 for our 3, than to start up the more efficient unit 1 for that particular period. We have seen that particular point, that the less expensive unit we have to turn on, because we have to consider on the total cost. So for that particular third hour, we have to concentrate on the total cost. So for the particular third hour, in order to meet the load demand, rather than going to the efficient unit, we have to go for the less expensive unit. So we will run the unit 4 rather than we will run the unit 1, that we have already seen in our discussion. So why we will run that? If I do the cost calculation for the hour 3, so by hour 3, it is clear that by hour 3, the difference in the total cost is 165, that is 0.014 rupees per megawatt hour. This is not an insignificant amount when compared with the fuel cost per megawatt hour for an average thermal unit with a net heat rate of 10,000 BTU per kilowatt hour and a fuel cost of rupees 2.0 MBTU, but a savings of rupees 165 every 3 hours is equivalent to rupees 4,81,800 per year. So rather than going for the efficient unit, we will go for the less expensive unit, which is not efficient, that is unit 4 for the third, in order to meet the load demand at the third hour. And for that purpose, using that conception, we will save the rupees 165 in every third hour, that is equivalent to that we have saved the rupees of 165 in every third hour, that is equivalent to rupees 4,81,800 rupees per hour per year, that is rupees 4,81,800 rupees per hour that we will save for the third hour. So this is the one of the important part, that is the total 8-hour trajectories. For the case 1 and the case 2 are shown in the figure 2. There is a total 1, 2, 3, 4, 5, 6, 7, 8, the 8 hour of the load trajectories. We are neglecting of startup and shutdown restriction in these two cases permits the shutting down of all but unit 3 in hour 6 and 7. So if the unit 3 has a minimum uptime of 5 hours. Unit 3 has a minimum uptime of 5 hours that is given in the data, and minimum downtime is 4 hours. And minimum 3 is the most reliable because its full load average cost is less. So we will run in order to meet the load demand unit 3 first. So if I on the unit 3 at hour 1, it will be remain on. It is called the minimum uptime, means minimum uptime is 5 hours. So we cannot offline the unit 3 before 5 hours. So means it is on at, if it is on at first hour, it will be on because it has a minimum full load average cost. So it will be remain on for 1 to 2, 2 to 3, 3 to 4, 4 to 5 and 5 to 6. This is the 5 hours. So at hour 6 it will be shut down, and it have to be remain shut down for for 4 hours because its downtime is 4 hours. So it has to be remain shut down for 4 hours. So it is clear that for the 8-hour load pattern, it is remain shut down. So we cannot bring back the unit before 4 hours. This is called the minimum downtime. So it is clear that if it is shut down at hour 6, so it will be remain shut down for hour 6 to 7 and 7 to 8. That is 2 hours. So that's why this is called that we neglecting the startup and the shutdown restriction in these two cases permits the shutting down of all units but unit 3 in hour 6 and 7. So this is the main conception behind that particular discussion. So again, these are the units, these are the state numbers, and this is the load pattern that we have already seen. And for the 8-hour load pattern, this load pattern is drawn here. Each of the hour, the load pattern is drawn here. 450 for first hour, for second hour it is 530, for third hour it is 630, for fourth hour it is 540, for fifth hour it is 400, for sixth hour it is 280, for seventh hour it is 290, and for eighth hour it is 500. And this is the state number from 1 to 15, and the corresponding unit status are given and total capacity are given. So the bold line will give the case 1, that is the priority order scheme, and the dotted line will give the case 2, that is the complete enumeration. So that we are starting from here, and we will see that in 12 state, that is state 12 is enough to meet the load demand of 550 for the hour 1 and hour 2. And also, but for the hour 3, the main difference is the hour 3. So first we will consider the case 1, that is the bold line. So bold line, we are concentrating on the priority order. So the priority order means we have to go from 12 state to 14 state depending upon the priority that we have discussed in our previous lecture. So now from here it is moved to state number 12. State number 12 to state number 14. Just follow the bold line. State number, that is the case 1, state number 12 to state number 14. Using the conception of priority listing. And again is come back to the state number 12 where the load demand is 540 for the hour 4. Load number is 540 for the hour 4, that is 12 state is capable enough to meet the load demand. Then the 400 for the sixth hour, for the seventh hour, it is, for the 400 for the fifth hour, for the sixth hour it is 280, for the seventh hour it is 290, and for the eighth hour it is 500. So it is seen that in the both cases, all the load demands can easily be met because the lines are clear nearly to the load demands. But now we are seeing the dotted line, that is the case 2. It is moved from state 12, it is start from here and it is for the hour 1 and 2, the state 12 is sufficient enough to meet the load demand. But here we are applying the conception of complete enumeration, means we are including the state 13, and we are also concerned about the cost. So rather opening, if I do the cost calculation that we have done in our previous discussion, with the help of that particular concept, we will have to do the cost calculation, and using that conception, we will see that rather opening the highly efficient unit, that is unit 1, we will rather committing the highly efficient unit or turn on the highly efficient unit, that is unit 1, we will turn on or commit the less efficient but uh, less expensive also the unit, that is unit 4. So that's why it is starting from here. Now I am following the dotted line. Now for the third hour, it is rather, it is using the conception of complete enumeration. It is going from state 12 to state 13. It is going from state 12 to state 13. It is going from state 12 to state 13, going from state 12 to state 13, going from state 12 to state 13, starting state at hour 3. Again, it is come back at hour 4 at state 12 and follow the same pattern for hour 5, 5th, 6th, and 7th hour. So only different is the hour. Difference will be found at hour 3, where the load demand is 600 and the board line where we are using the case 1, that is the strict, that is called the priority list method, and the second one, that is called the complete enumeration method, where it is denoted by the dotted line and only difference at hour 3. So the complete enumeration method, that will give the more search space to us, more search space to us. Complete enumeration method will give the more search space to us. So now we are moving to the case 3. So in case 3, the original unit data are used so that the minimum shutdown and opening times are observed. So here we are including a constraint or minimum shutdown and minimum updown. Means the minimum up and down time. For the forward dynamic programming algorithm were represented for the same interval load pattern, and we are used the conception of complete enumeration that we have done in our second case, that the complete enumeration was used. That is the upper bound on x and 3 different values for the n. The number of strategies that is saved at each states are 4, 8, and 10. And when only 4 strategies were saved, the procedure fails to find a feasible path in hour 8 because the lowest cost strategies in hour 7 have shutdown units that cannot be restarted in hour 8 for the minimum unit downtime rules that we have already seen, that if unit 2 is shut down at 6 hours, it cannot be turned on in 8 hours. So another, for the case 3, we are just complete enumeration that we have done in the second case. This is also we have to do for the case 3, but the difference is that we are introducing a constraint called the minimum up and down time. And another part is the upper bound, that is called the x, and where we are taking the different values of n, that is 4, 8, and 10, and that is called the number of strategies that saved at each state. So here the 2 variables that we are including, that is called x and n, that is included in this figure, where n equal to 3 and x equal to 5, where x is known as number of states to search each period, the total number of states, that is the number of states to search each period. And n is the number of strategies or path to serve each state. So here, if I see that 1, 2, 3, 4, 5, that is the x equal to 5, among those, the 3, that is 1, 2, and 3, from there the arrows are going out. Means for interval k minus 1, the total number of feasible conditions are 5. Among those, the number of state used is 1, 2, and 3. In case of the interval k, we will see the same thing, that 5 are used. Among them are three are used. Among the number of feasible are the 5. That is the x. That is the number of states to search in each field. And another is the interval k plus 1. So from interval k minus 1, it is seen that 1, 2, 3, 4, 5. That is the 5 number of total feasible conditions, or we can say the number of states to search each field is equal to 5. Among those 1, 2, 3, that is the number of states that we are used, or the number of strategies or path to be saved at each state. So we are now concentrating on the case 3, where we are introducing the conception of minimum up and down time. So unit 1, 2, 3, 4 are there. Minimum up times, that is for unit 1 is 4, unit 2 is 5, unit 3 is 5, unit 4 is 1. Minimum down times for unit 1 is 2, unit 2 is 3, unit 3 is 4, and unit 4 is 1. Minimum uptime and downtime means when a unit is in running condition. Say unit 3 has a minimum uptime of 5. So means it has to be run for the 5 hours. Before 5 hours, we cannot shut down it. Minimum downtime means, this 4 means for the unit 3 means it has to be offline for the 4 hours. Before 4 hours, we cannot bring it on to the system. So this is the load pattern. And that is the unit 1, 2, 3, 4 having maximum, and the minimum demands are for the unit 1 is 80 maximum demand, unit 2 250, unit 3 300, and unit 4 is 60. And the minimum demand for unit 1 is 25, unit 2 is 60, unit 3 is 75, unit 4 is 20. That is given that in the table. So we are using the conception of 8-hour pattern, that is our 1, 2, 3, 4, 5, 6, 7, 8, and corresponding states are given, that is from 15 to 9 here. All the states we can do for all the states, that is for the from the state 1 to state 15, and the English stackers are given, and corresponding the capacities are given. So we are starting from here. So it is clearly seen that the load demand is 450. So the capacity, summing those means it is unit for the 12 state, the unit, the complete numeration is done. That is why the 13th state is there. So we are now including the conception of minimum up and down time. So now for the 12 state, unit 2 and 3 is on. When unit 2 and 3 is on, the output power is 300 plus 250, that is 550. That is 550, and this can easily able to start the load demand of 450. For the second hour, the load demand is 530. It can easily be served with the help of this unit 2 and 3, that is the 12 state. Now, when we use the conception of complete enumeration, so the another conception is that which state we will use, 13 or 14, because for the 13th state we have to on the unit 4, for the 14th state we have to on the unit 1, from going from 12 state. If I go from 12 to 13 state, we have to on the unit 4. If I go to 12 to 14 state, we have to on the unit 1. So here are the constraint on minimum up and minimum downtime. So which unit will on? So if I on the unit 1, its uptime is 4 and its downtime is 2. But if I on the unit 4, its uptime is 1 and downtime is 1. So means at our 3 we can on the unit 4. If we on the unit 4, the unit 4 has a maximum demand of 60. So total output power is now 610, and it can serve the load demand of the third hour, that is 600. Means if I, and also it satisfies the conception of minimum uptime, that the constraint that it had, it also satisfies the constraint. So at hour 4 we can, the load demand is 540, that can be easily made by unit, made by the 12 state. That the 12 state means the total capacity is 550, so load demand is 540 at hour 4, and it can easily be made by the unit, the state 12. State 12 means unit 2 and 3 is on. So means we have to off when we move from our 3 to, when we move from our 3 to our 4, we have to off the unit. We have to move from state 13 to state 12. We have to off that particular unit, that is unit 4. So again, the conception of minimum downtime is there. Minimum downtime for the unit 4 is 1. So means we can easily turn off, or we can easily offline the unit 4. That is why the unit 4 is also on, because it has minimum uptime and minimum downtime. Both are 1 hour. So it can be up or it can be bringing to the line at third hour, and it can disconnect or offline at hour 4, because it has minimum up and downtime is 1. Both are 1, rather than going for the unit 1. That is, rather than going for 12 state to 14 state, we are moving from 12 state to 13 state. So for the hour 4, 5, 6, 7, 8, the load demands, that is 540, 400, 280, 290 and 500, that is easily served by the unit 2 and unit 3. That is because the output power is 550. So that is clearly seen in this figure. So that is why we can easily include the conception of minimum up and minimum downtime. So these cases can be summarized in terms of total cost found for the 8-hour period, as shown in this table below. These cases illustrate the forward dynamic programming method and also point out the problems involved in the practical application of the method. So in case of the case 1, where we are considering the priority order, where up and down times are neglected, the total cost is 73,439. 73,439. So the case 2, where the complete enumeration is done, where x is less than 15 with 4 strategies in set, that is the 4 strategies are set, up and down times are neglected, the total cost is given as 73,274. So at the third case, where x is less than equal to 15, and we are considering the up and down times are observed. If n equal to 4 strategies, there is no solution we will obtain. If n equal to 8 strategies, we are obtaining the solution. The cost is 74,110. 74,110. If n equal to 10 strategies, it is again 74,110. So this is the total cost for the case 1, 2 and 3. For case 1 it is 73,439. For case 2 it is 73,274. For case 3, where n equal to 4, there is no solution. Where n equal to 8 is 74,110. Where n equal to 10, that is 74,110. 73439 for case 1, 73274 for case 2. For case 3, when n equal to 4, no solution. For n equal to 8, 74110. For n equal to 10, it is again 74110. This is the summary of case 1 to 3, the total cost. So the unit commitment have forward dynamic method, that is we are starting the unit commitment by k equal to 1. So we calculate the fuel cost a comma. So we calculate the entire fuel cost in the second step. That is fuel cost, the total cost, that is k comma I equal to minimum of L, that is production cost ki plus startup cost from k1 minus 1 comma L is to k comma I, and we will do for all x equal to all states in period k. Then we come to the second third part, that's k equal to k plus 1, and we will find the a, that's the n feasible states in interval k minus 1. Again we will calculate the fuel cost, total cost, that is k comma I, that's minimum of production cost, that is k comma I plus startup cost, or we can say the transition cost, that is k minus 1 comma L is to k comma I plus fuel cost of the previous case, the fuel cost that is calculated here, it will come back, it will come to here, that is k minus 1 into L, and we will do it for all its states in period states I in period k. So we will save in lowest cost strategies, the lowest cost we will save if k equal to m last hour. If it is no, then we will route it back to that particular portion, that is k equal to k plus 1, or otherwise if it is yes, then trace the optimals. If it is no, we will get back that portion. If it is yes, then it is the trace the optimal schedule and we will stop the algorithm of the dynamic programming. So today we have learned the dynamic programming solution, where we will consider the complete enumeration, that is denoted at case 2, and also the minimum up and down time, that is denoted as case 3. And we will see how the cost is varies for each case 1, case 2, and case 3. How the cost is varied for the case 1, case 2, and case 3. That is for the priority order scheme, that is case 2, case 1, priority order scheme, that is case 1, case 2 is the complete enumeration, case 3 is the include. We are including a constraint for minimum up and down time, how the total cost is varied with the help of dynamic programming solution. Thank you.